Hello everyone, I'm gonna get started pretty soon here. Alright, so today we'll be going over U-Substitution. It mostly has to do with antiderivatives and integrals and such. So when it comes to integrals, we have two types of integrals generally. We have indefinite integrals and definite integrals. So indefinite integrals are generally just antiderivatives. So you have the integral of f of x dx, for example, and you would get the antiderivative of f of x, big F of x, plus some constant c. So generally you won't get a complete answer because you'll always have that constant that integration can't really account for. But that is different when you have a definite integral. When you have a definite integral, you have some sort of bounds of your function from a to b of f of x dx, and you'll be able to calculate that integral by using big F of b minus big F of a. So you don't have that kind of unknown constant there. And it's actually called the fundamental theorem of calculus. When f of x is continuous on a closed interval from a to b, you know that answer is big F of b minus big F of a. Alright, so a small little review of differentiation and integration. So you have to calculate the derivative of x squared, for example. Pretty straightforward. You can just do a power rule. So that it's going to be 2x. And if we have to do the integral of 2x dx, this would be an indefinite integral. We just basically do a reverse power rule. So it would be 1/2 times 2 x squared plus c. So you notice that these are kind of two of basically the same. So the first one we're doing we're differentiating x squared, and we get 2x. And integrating is basically the opposite of differentiating. The only discrepancy is that c, and that's kind of what we're interested in with U-substitution. Is that we'll see that doing U-substitution is kind of like the inverse of doing a chain rule. So when you're doing a differentiation, you do a chain rule when you have basically a function within a function. And you'll see that the U-substitution you use to kind of do a reverse chain rule almost. So here on our next equation, we have d over dx of 1/6 quantity 2x plus 2 to the third plus 12. So when we're differentiating this, we can kind of pull out that the coefficient 1/6. We also aren't really too concerned with that plus 12 because when we differentiate a constant, it just becomes 0. So this is really just asking what is 1/6 times d over dx of quantity 2x plus 2 to the third. And in this case, we have to do a chain rule. So we have this quantity to the third. So that'll be our first derivative. So it'll be so quantity to the third. The derivative of that is going to be 3 times that quantity squared. So just a little power rule. So we'd have 3 times 2x plus 2 squared. And then we have to multiply that by the derivative of the inside, which is just 2. And that whole quantity is multiplied by that initial 1/6. So multiply everything out. The 3 times 2 makes a 6. Kind of cancels with that 1/6. So our answer would just be the quantity 2x plus 2 squared. All right, this next example, again, just doing the chain rule. So we'll have the derivative of 2/3 e to the x to the third plus 3. Again, we can pull out that coefficient 2/3. We can more or less ignore that that term of 3. So this is just 2/3 times d over dx, quantity e to the x to the third. So again, we'll just do a chain rule, which will give us 3x squared. Oops, I'll go ahead and put a little equals in there. So 3x squared times the quantity e to, I guess it would be that whole function that we're interested in, x to the third. And knowing our differentiation rules, e to anything, or I'm sorry, e to the x, the derivative of e to the x is just e to the x. So this would be 3x squared times e to the x to the third. And then we have to multiply the whole quantity by that initial 2/3, which would give us 2x squared e to the x to the third. All right, and then here's one other little integration rule that I'm sure you guys have learned. You'll see we have the integral of the quantity 5x to the fourth plus cosine of x dx. So in this case, we know that we don't have to use U-substitution because it's not a product of two functions of x. So we can really just write this as the integral of 5x to the fourth dx plus the integral cosine of x dx, and can do two separate integrals, which would just give us, let's see, do a quick little integral. It would be x to the fifth plus, it would be sine x plus our constant c, which we have to remember because it's an indefinite integral. All right, so using U-substitution. So in this function down here, we know that we have to use U-substitution because we can't break up this integral. When it's a product of two functions of x, we have to use, we can only integrate with respect to a function of one with one factor of x. So what we'll have to do is we'll have to sub in u for x to the fifth to eliminate that factor of 5x to the fourth, and that'll give us an integral in just terms of u, and then we'll be able to fully integrate that. All right, so just to illustrate what I mean, we have the integral of quantity 2x plus 2 squared dx. So we don't have to use U-substitution, but it will make our lives easier. In this case, we can just multiply out, 2x plus 2 times 2x plus 2, and that'll just give us, an x squared plus an x plus a constant, and we can integrate that pretty easily. So let's see, 2x plus 2 quantity squared will give us 4x squared plus maybe 8x plus 4. So we can go ahead and integrate that with respect to x. So integral of 4x squared plus 8x plus 4 dx. That's just going to be a bunch of reverse power rules, which is going to be 4/3 x to the third plus 4x squared plus 4x plus some constant. So now we have this big equation for our big f of x, you could call it. And it's kind of not what we want. We want things to be simple. So if we use a U-substitution, we'll see that we'll get an expression that's not expanded. It'll make our lives a little bit easier, especially when we're working with higher power functions. So our U-substitution that we would do is we would set U equal to our 2x plus 2. So then we'll take a little derivative, du. It's going to be 2 dx. And we want to solve for dx so that we can plug it into our original integral. We just do that by dividing both sides by 2. We get dx equals du over 2. Now we substitute our u and our dx into our original integral. So we have the integral of u squared du over 2. So we can pull this over 2 out because it's just really just a coefficient. So our integral is 1/2 times the integral u squared du. From here, we'll just do a antiderivative real quick. So it'd be 1/2 times 1/3 u to the third. And then it is an indefinite integral, so we'll add that little c at the end. And then we multiply out our 1/2 times 1/3, we get 1/6. We plug back in our u, which is 2x plus 2, and it's to the third power, plus c. So if we did expand this out, it would give us this exact same answer from this first part without U-substitution. But for example, if this were a definite integral, we would have 2 points to plug in. We'd use the fundamental theorem of calculus. And on this first part, without U-substitution, we would have that whole equation 4x, or that whole expression, 4 over 3x cubed plus 4x squared plus 4x plus c. We'd have to plug in our intervals twice into that. So we basically have to do 3 times as much work, whereas we just plug in one value for x for f of b and one value for x for f of a when we use U-substitution. All right, and here's an example of, I just changed the power. I increased the power from being quantity 2x plus 2 squared to 2x plus 2 to the fifth. And you'll see that if we do U-substitution, we use the same u, we use the same dx, we would get 1/2 times the integral u to the fifth du, which would give us 1 over 12 u to the sixth plus c. So that's a lot more simple. It's a lot more straightforward and simple than multiplying 2x plus 2 by itself 5 times and then integrating that whole crazy expansion. All right, so we'll just go ahead and do a couple more examples of U-substitution, get some good practice in. All right, we have the integral 3x squared times quantity x cubed plus 3 quantity squared dx. So generally with these U-substitutions, you want to find the term that has the highest power x, and you want that to be your u. That way when you take a derivative of that u, you'll be able to cancel out the smaller term x. So in this case, we choose u is x to the third. Come on. X to the third plus 3. So our du, just do a quick derivative, is 3x squared dx. And again, we want to isolate dx to plug into our original integral. We have dx equals du over 3x squared. Put that back into our original function. We have the integral of 3x squared times, well, we chose that to be u, our x cubed plus 3. So that'd be times u squared. And we'll multiply by what we found dx to be, which is du over 3x squared. And this is a pretty straightforward example, so we see that we have a numerator of 3x squared and a denominator of 3x squared, so those cancel out. So we're just left with the integral of u squared du. We can just do a simple, straightforward antiderivative, which will give us 1/3 u to the third plus c. And then we'll plug back in our u. And we'll get our answer 1/3 times the quantity x cubed plus 3 plus some coefficient, or I'm sorry, plus some constant c. All right, here's an example of a definite integral. So we'll have our final answer will be missing that constant c, but we'll know we'll know exactly what our answer is. Let's see. It's a little bit more complicated example, but we do see that x cubed is probably what we want to use for our u. What does u equal? In this third one, in question 3, so in this example we set u equal to x cubed plus 3 that we plugged into our integral there. Someone was asking what u is equal to. Just want to make sure it was on the same page. Okay, yeah. So u is x cubed plus 3. That's the highest power x. That's why you want to choose u. And then we'll take a derivative of that. We'll get our du equals 3x squared dx. And then we plug that back in, and then we do an integral, or we integrate antiderivative of u squared du, and that'll give us 1/3 u to the third plus c, and then we just plug back in this original value for u. So that gets plugged in there. Oh, so in number 2, it's the same integral as number 1, except the power is 5 instead of 2. So we can just use the same u. So for part 2, we would choose u equals 2x plus 2, du equals 2 dx, dx equals du over 2, which is the same as up here. But in this case, we have a power of 5. Missing cube. Oh. Over here? Missing cube for x to the uncertain of the missing cube for quantity x to the third plus 3. Oh, I see, yeah. Okay, yeah. So the final answer does have that. Oops. Yeah, the final answer is that quantity squared. Or I'm sorry, it's cubed? Yeah, because we did an antiderivative, so it's cubed. So it'd be 1/3 quantity x to the third plus 3 to the third plus c. I see. Thank you. All right, I'll go ahead and move on to the next one. So in this case, we want to choose our u to be x to the third. So then our du would be 3x squared dx. And we'll go ahead and isolate dx by dividing by 3x squared. We'll have dx equals du over 3x squared. So we'll substitute, well, so we have our u and our dx. In this case, we're working with a definite integral. So our 0 and 5 are in terms of x, and we actually want to modify those to be in terms of u. So if we plug 0 in for x, our u would still be 0 because it's 0 cubed, which is just 0. But when we plug in 5 for x, our u will actually equal 5 to the third. So in this case, x equals 0 will imply that u equals 0, and when x is 5, u will be 125 because that's 5 cubed. So we have to just change our interval there to match u. So that'll make our interval 0 to 125, and we plug in our u, which would be e to the u times du over 3x squared. So our x squareds will cancel out. We'll be left with 2 over 3, which we can pull out of the integral. So we have 2/3 times the integral from 0 to 125 of e to the u du, which we know the derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x plus a constant if you're an indefinite integral. In this case, we'll go ahead and use the fundamental theorem of calculus. So it'll be 2/3 times the quantity EU evaluated from 125 to 0, which is 2/3 times the quantity e to the 125 minus e to the 0. And e to the 0 is just 1. But we can go ahead and leave that as our final answer. So if the x squareds didn't conveniently cancel out, you could, if it is solvable through U-Substitution, one little trick that you can do is you can find You can find whatever that extra factor is, like let's say it's an extra x squared. You could find that in terms of u, or let's say, so an example where maybe we had u equals x to the fifth plus 5, you could say that x to the fifth is equal to u minus 5. And then you would try and substitute u's in for that x, that whatever that extra factor of x that you would have. That is if it's solvable through a U-substitution method. That's like a little aside. All right, I'll go ahead and do another example of a definite integral. So in this case, we have from 0 to root pi of 10x times minus sine of 2x squared dx. So in this case, we want our u to be that quantity inside of our trig function. So we'll say u equals 2x squared, which means our du will be 4x dx. And then we'll solve for dx, which will be du over 4x. All right, so again, since it's a definite integral, we have to evaluate our parameters a and b for our u. So again, put in 0 for x, u will still be 0. So x equals 0. That'll give us a u of 0. And then when x equals root pi, our u will be 2 pi. So go ahead and change our interval in terms of u. So it'd be 0 to 2 pi. And then we'll plug in our u where it's applicable. So we have 10x times negative sine of u times dx, which is du over 4x. All right, so our x's cancel out. We'll pull out that 10 over 4, which is just 5 over 2, and pull that out of the entire integral. So we have the 5 over 2 times the integral from 0 to 2 pi of, let's see, that would just be sine of u du. Oh, I'm sorry, there's a negative sine u du. So the antiderivative of that is just going to be cosine of u. So let's give ourselves a little bit more space. We'll have 5 over 2 times the quantity, be cosine of u. So antiderivative of negative sine u is cosine of u. We're going to be evaluating that from 0 to 2 pi, which means we'll do the fundamental theorem of calculus. 5 over 2 of cosine of 2 pi minus cosine of 0. So when we evaluate each of these trigonometric functions, cosine at 2 pi and 0, it's actually going to give us 1. So it's just going to be 1 minus 1, which is 0, times 5 over 2. So our final answer for this actually is going to be 0. And when you start learning about integrals in terms of like an area under and above a curve, basically what that means is, from a graphical standpoint, this has just as much area above the curve as it does under the curve. So it might look something like that, where this shaded region is going to be equal and opposite to that shaded region there. It's kind of interesting. All right, so this last one that I have prepared, another definite integral from 1 to 3 of x cubed plus 3 over x to the third plus 9x dx. So in choosing our u, we want to choose the x with a higher power. That way we can try and just get our whole integral in terms of 1u. So we'll say u equals x to the third plus 9x, which means our du will be 3x squared plus 9 dx. Again, we'll want to find dx, so we'll just divide by 3x squared plus 9. We have dx equals du over 3x squared plus 9. Then we'll plug in our u and our dx into our original integral. But first, we'll find our parameters, our a and our b, in terms of u. So our lower bound, our x equals 1. When we plug that into our u, we would have 1 cubed, which is 1, plus 9 times 1. So it'd be 1 plus 9. Our u will equal 10. And then our b, our second value, is 3. So we put 3 in for x in our u equation. We have 3 cubed, which is 27, plus 9 times 3, which is also 27. So we have u equals 27 plus 27, which is 54. All right, so we'll put that back into our integral and sub in u and dx. So we have the integral from 10 to 54 of, we're going to separate this as a factor of x squared plus 3 times 1 over x cubed plus 9x, which is going to give us 1 over u. And then we have dx, which in this case we found to be du over 3x squared plus 9. Okay, yep. And then let's see. So we can actually pull out a factor of 3 from this denominator over here, which is to say that 3x squared plus 9 is equal to 3 times the quantity x squared plus 3. So when we multiply that by our initial x squared plus 3, we just get 1 over 3, which we can pull out of our integral. So we have 1/3 times the integral from 10 to 54 of 1 over u du. All right, so the antiderivative of 1 over x is going to be the natural log of the absolute value of x. So in this case, let's go ahead and bring it over to the side here. So we do an antiderivative of 1 over u, we get ln u. So we'll have 1/3 times the quantity ln absolute value of u evaluated, oops, no, go back down. All right, we evaluate from 10 to 54, which means we'll have 1/3 times the quantity ln 54 minus ln of 10. And that would be the answer for our definite integral. and number 6. All right, so that's something important that you want to do with the definite integrals is that, I suppose there is 2 ways that you can do it. Generally, the preferred way is that when you use U-Substitution, you'll find your integral, the endpoints of your integral in terms of u, but it is possible to go ahead and substitute your initial u in. So in this case, we would substitute x cubed plus 9x without changing our integral domain, and then we would calculate it in terms of x rather than calculate x in terms of u, and then find our integral from 10 to 54 in this case. All right. I think that's all I have for examples. I guess I'll go ahead and open up the floor, see if anyone has any questions. Do my best to answer them. If not, we could maybe change some of these indefinite integrals into definite integrals and then see if we can solve. Let's try that. All right, so I'll use the example from number 3, but I'll set it up as a definite integral. Oh. Don't understand how you got integral of 1 over u. Sure. Okay. So in this one, so we want to choose u as the highest power of x. So in that case, it's our entire denominator here. So we have x to the third plus 9x. So we set that to be equal to u. And then we'll find du and in turn find dx. And we plug that back in. So the transition from here to here. So we have to change our integral, our a and b, from 1 to 3 in terms of u, which in this case is 10 to 54. And then our fraction here, our x squared plus 3 over x to the third plus 9x, is really just x, this quantity here, times 1 over x to the third plus 9x, which is this 1 over u. So we just separated our fraction into a product of 2 expressions. That's how we get 1 over u. And then when we plug in our dx, we get 3x squared plus 9, which gives us this 3 times the quantity x squared plus 3, plus, and then that will cancel out with this term, this expression x squared plus 3, which will just give us 1/3 times 1 over u. And we can pull that 1/3 out because it's just a coefficient, a constant. And that'll give us the integral from 10 to 54 of 1 over u du. Did that make sense? Okay, cool. All right, so I don't have any other questions. I'll go ahead and I guess change one of these indefinite integrals to a definite integral, and then we can solve from there. Oh. Indefinite integral. Let's see. So I have the indefinite integral of x. X plus 1. Let's try that one more time. I believe that's the question. Let's see, an indefinite integral with integrand x, quantity x plus 1 to the 10th. So we have u equals x plus 1, du equals dx. So I guess our x would equal, so this is the trick that I was talking about earlier. We can change this x in terms of u by using our u equals x plus 1. So you would subtract 1 from both sides, you get x equals u minus 1. So that would leave our indefinite integral. So x becomes u minus 1, so we have u minus 1, and then our u, which we plug in for x plus 1, would be u to the 10th dx. And then you would just multiply that out, so you get the integral u to the 11th minus u to the 10th. Oops, that shouldn't be dx, that should be du. In this case they are equal, but I do want to be careful with that. So that's du. Should bring du down here. And then we just do power rules, or reverse power rules. So we have the integral from be 1/12 u to the 12th minus 1/11th u to the 11th. I'm sorry. I already did the integral. I already did the antiderivative, so yeah, after we do the antiderivative, we would get 1/12 u to the 12th minus 1/11 u to the 11th plus our constant c. Du, yeah. And then we would plug back in our x plus 1. So you get 1/12 x plus 1 to the 12th minus 1/11th times x plus 1 to the 11th plus c. So again, the little trick that we did here was we had this x that didn't cancel out when we plugged back in our dx du. So we had to set our u. So right now we have u isolated and it gives us x plus 1. That's what we chose. And we want to eliminate that x. So we just put x in terms of u. could we subtract u to the 10th from u to the 11th? So I don't believe that's correct. So when we plug in, so in this second step right here, let's see. We're just plugging in our values for u and x that we found over here. So we plug those into that second integral, and we multiply this u minus 1, which is x, times u to the 10th, which we found up here. And when you multiply that out, it gives us u to the 11th minus u to the 10th. If you wanted to do u to the 10th minus u to the 11th, then you have to multiply the whole thing by -1. So if you multiply this expression, this integral, by -1, let's see. I suppose you could do it, but it'd be a little bit roundabout. So you had -1 times the integral of u to the 10th minus u to the 11th du. Yeah, you can't subtract things with different powers. That's true. Yeah, if you really wanted to expand u to the 11th minus u to the 10th, you could, but it wouldn't be fun. Because as you see in our answer, our u is x plus 1, so you'd be doing a pretty large Pascal's triangle for that one. All right, I'll go ahead and start working on another one. Oh, I do have that one looks kind of complicated. We'll give it a try. Let's see. So we have the integral integral 18x to the 5th times the quantity, let's see, times x to the 3rd minus 5 to the 4th dx from -1 to 1. Okay. I just want to double check, make sure I copied that right. All right, so pretty sure I have that right. I have u equals, yeah, you'd set u equal to the, well, I guess in this case it wouldn't be the largest power. Okay, so I guess not in every case you want to do the largest power. I think you do the smaller power on this one. Well, I guess it would be the largest power because it's under the, so it'd be x to the 3rd minus 5 to the 4th. So it kind of is the largest power since that whole quantity is to the 4th. So we'll get du equals 3x squared dx, which give us a dx equals du over 3x squared. And then we also have to change our interval in terms of u. So when x equals -1, u would be, so -1 to the third would be -1. It would be -6. When x is 1, u would be, so it would be 1 minus 5, so it would be -4. So our integral would be from -6 to -4 of 18x to the 5th times u to the 4th times du over 3x squared. All right, so we do cancel out two factors of x, and then 18 over 3 is going to be 6, so we can pull that out. Let's see, I'm going to need a little bit more space on this one. So we have a 6 times the integral from -6 to -4. So x to the 5th divided by x squared is going to be x cubed. So we have u to the 4th du. And then I think we have to do that trick again where we find x in terms of u. So we go back up to our u equals x to the 3rd minus 5. We'll add 5 to both sides. We'll get x to the 3rd equals u plus 5. And then we plug that back in, and we get 6 times the integral from -6 to -4 of u plus 5 times u to the 4th du, which equals 6 times the integral from -6 to -4 of u to the 5th plus 5u to the 4th du. I'm going to go ahead and do an integral or antiderivative. So we get 6 times the quantity. Let's see, it'd be 1/6 u to the 6th plus, so it'd be 5 over 5, so it'd be u to the 5th. And we'd evaluate that from -6 to -4. Just grab a calculator real quick. So let's see. So first we'll plug in -4 for u. So we have -4 to the 6th times 1/6. So I got a -682.67 repeating, plus u to the 5th, so -4 to the 5th, which would be minus, oops, so it'd be minus 1024. So that's all times 6. Well, so that's our big F of B, and we'll subtract our big F of A, which is going to be -6. Let's see, 6 times -6 to the 6th. Or no, it's 1/6. 1/6. So that'd be 7776 plus, it's going to be negative would be negative negative 6 to the 5th. I suppose it's basically the same thing, isn't it? Since we're dividing by 6 in that first one. So that whole part's actually just going to be 0. So it'll be plus a negative 7776. Give myself a little bit more space here. So we have 6 times, so this whole, so f of a is going to be, big F of a is going to be 0. So we're really only interested in f of b, so I just want to be 100% sure I got that one right. So it'll be negative 4. Negative 4 to the 6th. And then we would divide by 6. So that's negative 496 over 6 plus a negative, which I'm sure this is, negative 4 to the 5th, which is 1024, which is correct. So that whole quantity times 6, so it's going to be negative 4096 minus 1024 times 6. Which is 6,144. So I believe the answer is going to be negative 10,240. So again, in this one, you have to use that trick where you have that extra factor of x when you do your initial U-substitution right here. So you divide out that x squared, and you'll still get an x to the third, but we use our u equals x to the third minus 5 to get x cubed equals u plus 5 over here. And we plug that in, then we get our integral just in terms of u. Let's see what the internet says about this one. Looks like I may have made a slight error in my calculation. I'm going to double check my big F of A. So that would be when you plug in negative 6 into our antiderivative. It's going to do this with negative 6. So negative 6 to the 6th. And divide that by 6. still got negative 700. Wait, are they both gonna be negative? Is that what it is? Okay. I missed a negative sign. No, it's to the 6th, isn't it? So it should be positive since it's a even parity. I'm certain I did the process right. I just didn't get quite the correct answer. It should be a positive value, I believe. No, it's a negative value. It's negative 2048. Let's see, 6,144 minus 4096. Maybe this is supposed to be plus. I did do the process right. I'm not sure if I got exactly to the right answer. Hopefully that helped you. But I do believe that the main trick to this one, aside from your standard U-substitution and definite integrals, is that you want to plug in that x to the third is equal to u plus 5. So you find that extra x to the third in terms of u. All right, I think that just about wraps it up for tonight. Let's see. 5u to the 4th. So I didn't evaluate anything to the 4th power. So when I do the antiderivative here, I get u to the 6th, 1/6 u to the 6th plus u to the 5th. So whenever I evaluate u to the 6th, since 6 is even, it should give me a positive number. And when I evaluate u to the 5th, it's odd, so it should give me a negative number, since u is negative in both cases. Guess we can always start it over and try again. Let's see. So we have 6 times the integral from negative 6 to negative 4 of u to the 5th plus there's 5. 5u to the 4th. No, I counted for that. Du, and then we did the antiderivative. Be 6 times the quantity 1/6 u to the 6th plus u to the 5th, evaluated from negative 6 to negative 4. Okay, so this is 6 times 4,096 over 6 plus -4 quantity -4 to the 5th. Just going to be minus Alright, let me do our minus our f of a, which is -6, so we put in -6 for u. Quantity -6 to the 6th, divide by 6. $700 or 7,776 plus u to the 5th, which is going to be quantity -6 to the 5th. Yeah, I still got that to be 0. But I must have missed a negative sign. Got 4,096 minus 6,144. Okay, there we go. That's the right answer. Yeah, I think I just had an extra negative sign in there. All right, cool. I'll go ahead and wrap it up then. Thanks for tuning in, guys. Have a good one.